So it's a great pleasure to have Louise here today. Thanks a lot for accepting our invitation. Louise is currently an ESA Research Fellow at the Space Telescope Science Institute. She obtained her PhD in 2021 from Paris Observatory, where she studied Cepheids distances using Gaia and the Cepheids metallicity dependence. After that, she joined the SHOES team at the Johns Hopkins University, where she worked on Hubble Space Telescope observations of Cepheids. And in 2025, she moved to the Space Telescope Science Institute as an ESA Fellow, where she investigates the systematics of primary distance indicators. Today, she will present recent improvements to the Cepheid supernova distance ladder with HST and JWST. Louise, please, you can start when you're ready.
Thank you so much, Eleonora. It's a pleasure for me to be here today and present my work. So this is work in collaboration with my colleagues listed here. And today I'm going to talk about Cepheids and how they're used in the distance ladder for measuring H0 and recent improvement with the Hubble Space Telescope and the James Webb Space Telescope. All right, so first of all, I'm going to give a short overview of how Cepheid distances are measured and what are Cepheids. Cepheids are pulsating stars, which means they're pulsating like physically. There's a opacity variation in the outer layer of the stars, and these pulsations are extremely regular. It's not only a change in the brightness, but it's also a change in the color, in the temperature, and in the radius. So basically what we do as astronomers is we do time series to measure the brightness variation, and we produce light curves. We measure the pulsation periods. And Cepheids in the HR diagram are located in the instability strip along with other pulsating stars. So Cepheids are standard candles, which means they can be used to measure distances. And this feature was discovered by Henrietta Leavitt 100 years ago by looking at photographic plates of especially the small and large Magellanic Clouds. So because she didn't have any software to measure the photometry of stars, she had to use a reference plate such as this one, where the stars were labeled according to their brightness and then compared between different plates to measure how bright they are. So what Henrietta Leavitt did was to classify all these stars, and today I want to give a special to show why Cepheids are used today and how we ended up using them. It's completely thanks to this work. And a few months ago, we decided with Caroline Wong and Adam Rees to take a close look at this and reanalyze it completely and compare it with modern data. So basically what you see here, the first column is basically the date of observation. The second column is the plate number. And then each column is a pulsating star or a Cepheid. And you can see that based on her plates, she could see that they were varying in brightness by eye. So what we did in our reanalysis is that we produced the light curves, which had never been produced before. And we can actually see the brightness variation, and it's very clean. There's some scatter, but you can see the light variation. And if you look at the same objects today with modern telescopes, for the exact same stars, you can see the same light curve shape. The only difference here is the amplitude, because the photographic plates used by Leavitt are bluer than the V-band, and the amplitude is a function of wavelength. So that's the only difference. Of course, the scatter is much better now, but considering the technology she had access to, it's quite remarkable to see how good she could already measure the light curves, even though she did not publish them. So if you're interested in learning more about this discovery and the work Leavitt did 100 years ago, you can look at this paper, which is a reanalysis of this discovery. All right, so based on her notebook and all her observations, she made this discovery that Cepheids exhibit a relationship between their pulsation period here on the x-axis and their brightness. So the bottom line is the minimum brightness for a sample of Cepheids. And then for the same stars, the top line is the maximum brightness. So it's a bit confusing because sometimes, right now we use only one line, which is the mean magnitude, but for her discovery, she shows the minimum and maximum separately. And what she says in her paper is that the brighter variables have the longer periods, and that's what we call today the Leavitt law, or the period-luminosity relation in this form. So basically, two Cepheids, no matter where they are in the universe, if they have the same pulsation period, they should have basically the same intrinsic brightness. So a difference in apparent brightness would be a difference in distance, because, for example, a star twice as far would be 4 times fainter. And this relationship is really well understood today from the physics point of view, because the pulsation period is correlated to the density of the star, and also using the Stefan-Boltzmann law, the luminosity is connected with the radius and the temperature. So that's something we both understand theoretically, and empirically we measure it really well. So that was her discovery. And the impact of her discovery was to solve the great debate, to answer the question whether the nebulae are outside the Milky Way or a part of it, and discovering that there are many more galaxies outside the Milky Way, and eventually helping Edwin Hubble to discover the expansion of the universe in 1929. And in this Hubble diagram, the first one, I believe, the velocity is measured from spectroscopy, and the distances are partially based on Cepheids and the discovery by Henrietta Leavitt. All right, so how do we use Cepheids now? Technically, how does it work? So the first step is first to calibrate the period-luminosity relation where you have known distances. So for example, in the LMC, we know the distance of the LMC. So you observe the Cepheids, you take a sample, and you get from light curves, you get the pulsation period, the apparent magnitude. Usually we take the mean. And then knowing the distance, you calibrate the period-luminosity relation, which means you calibrate the coefficients A and B. And now to apply it to other galaxies where you don't know the distance, you also measure Cepheids, you get light curves and pulsation periods and apparent magnitude. And then basically the difference in intercepts is a difference in distance modulus. So that gives you a relative distance between two galaxies. And something else you can do if you don't want to have relative distances, but you want absolute distances, you need to calibrate the absolute period-luminosity relation. And that you can do with geometric distances. The first possibility is to use parallaxes in the Milky Way. First, this has been done with spatial scanning by the Schu's team, or for a larger sample with Gaia. So basically, the movement of the Earth around the sun gives you a different angle to see a star, and the larger the movement, the closer the star is to you. The other method in the Magellanic Clouds is eclipsing binaries. It's completely independent of parallax, and it's a purely geometric method. And the last method is to look at masers. This is in NGC 4258, and these 3 galaxies, which have independent distances, are what we use right now as the anchors of the distance ladder. So the anchors to anchor the period-luminosity relation of Cepheids, which leads me to the Cepheid and type 1a supernovae distance ladder. So the ladder is made of 3 rungs as of 2022, but later I'll get to the recent improvements. So as of 2022, it was made of 3 anchors, Milky Way with Gaia parallaxes, LMC, and NGC 4258. These are known distances, geometric distances. Then we move on to the second rung, where we observe both Cepheids and type 1a. And then we use Cepheid distances to calibrate type 1a. This is limited to the volume where we can observe Cepheids because they're fainter than supernovae, and also limited by the number of available type 1a supernovae. And finally, the third rung, we look at redshifts and distances of type 1a to get to the Hubble constant. This needs to be far enough to avoid local interactions, but close enough to measure H0 today, so the local Hubble constant. Something that the SHOES team has been working on is focusing on consistent photometry for Cepheids between the first and the second rung. So all of the Cepheids are observed consistently with the Hubble Space Telescope. So there's no photometric systematic. So this is a plot from RIS 2022 showing the 3 anchors with 3 independent geometric distances. And then the main improvement in the SHOES 2022 release was the doubling of this second rung sample to now 42 supernovae calibrators. You see the histogram of how much we've been observing them in the past years. And then finally, the Pantheon supernovae on the last rung. In the SHOES distance ladder, we use the near-infrared and colors to minimize the effect of dust. We use a simultaneous fit of the 3 rungs together with 5 free parameters, the Cepheid and supernovae luminosity, the slope of the PL, gamma, which I will cover later, is the dependence with metallicity, and finally H0. And all these rungs are measured consistently. Again, especially Cepheids are measured consistently with the Hubble Space Telescope, which gives a Hubble constant of 73 plus minus 1. Again, as of 2022, but today I'd like to highlight a few improvements, especially I work on the first rung in particular and improving the geometric distances and Cepheids here on the first rung. So the first thing I'd like to mention is how we improve the Milky Way calibration. These are Gaia parallaxes of individual Milky Way Cepheids, but we can do something even better than using individual Cepheids, is we can use Cepheids in clusters. And I'm talking about open clusters in the Milky Way. So clusters, they host more than 100 stars, which means if you average the parallax of their members, you get a much better parallax for the Cepheid they host. The other good thing about clusters is that the members are generally fainter and they're less sensitive to Gaia systematics, and they're better calibrated because in the Gaia catalog, there are more faint stars, so they're more common. What we did with the SHOES team is that we observed 17 cluster Cepheids, and they're as good as 75 individual Cepheids because their parallaxes are overall 3 times better, more precise. And we observed consistent HST photometry. Even if these Cepheids are very bright, we observe them with spatial scanning to avoid saturation, which is again a very consistent way to get the photometry. And we obtain a very tight PL relation shown in red here for cluster Cepheids as compared to in gray individual Cepheids. So using this small sample of cluster Cepheids, we are able to improve a little bit the Hubble constant. And for the first time, we go below the 1 kilometer per second per megaparsec in the uncertainty. That's something we published in 2022, right after the SHOES 2022 release. And then the second improvement I'd like to mention today in the first rung is the addition of a new anchor. So as of 2022, there were only 3 anchors, Milky Way, LMC, and NGC 4258. And so far, we haven't been able to include the Small Magellanic Clouds for different reasons. But in 2020, the Araucaria project published a geometric distance to the Small Magellanic Cloud with eclipsing binaries shown in yellow. So we selected Cepheids in the core to avoid depth effects. I'll get back to this later. But basically, we select Cepheids in the core and we observe them again consistently with HST to be able to include them in the distance ladder. And we obtain a beautiful PL relation here. And because the SMC is so nearby, there's no crowding, there's no contamination from the background. And compared to ground-based measurements, we reduce the PL dispersion from 0.15 to 0.10 mag. And including this SMC as the 4th anchor of the distance ladder, again, we reduce the uncertainty in H0. So I mentioned the depth effect because the SMC is very elongated along the line of sight. So whether you include the whole sample of Cepheids or if you limit to the core, you won't get necessarily the same PL relation, especially the scatter is different. So the whole sample gives you a larger dispersion, but if you limit to the core, you are able to reduce the dispersion of the PL relation. And there are two different lines here, is with and without additional geometry correction. This is another improvement we can make by accounting for the exact position X, Y, Z of each Cepheid in the Small Magellanic Cloud, so their depth compared to the rest of the galaxy, using, for example, the distribution of eclipsing binaries as shown here. So basically the recommendation is, yes, you can include the SMC as an anchor if you respect these two conditions, you limit to the core, and you apply the geometry corrections, and you should not suffer from any depth effects if we do that. All right, so now the distance ladder gives a Hubble constant of 73.17 plus minus 0.86, combining the 4 anchors and the 42 supernovae hosts. These are all the variants that have been tested in the last SHOES release. The bottom line is that it's really hard to get below 72 and higher than 74. Here I'm listing a few of the Cepheid variants, so choosing only optical photometry or closest hosts, assuming no metallicity effect, or assuming a break in the PL. Whatever we pick, it's really hard to deviate from the baseline. And the scatter of these variants is included as a systematic in the value. All right, so as you know, there's this Hubble tension, but it's not just between SHOES and Planck, it's between the early universe measurement and the late universe measurements. So there's of course SHOES that gives the best constraints. But there's also TRGB measured with JWST. There's the SBF, TRGB SBF method. There's the DESI fundamental plane, the TD Cosmo more recently. So it's really, there's really a good agreement between all these methods around 73. So now that we have this Hubble tension, what we're interested in is testing whether there still are systematics, like unknown systematics in Cepheid distances. And there are two main systematics that I'd like to discuss today. The first one is metallicity, and the second one is crowding. So when I say systematics in Cepheid distances, the question is, when we observe Cepheids in the first and second rung, are we observing the same thing, and are we observing them the same way? And it's not necessarily the case, because LMC and SMC Cepheids are more metal poor than supernovae hosts. And we know that metal-rich Cepheids are brighter than metal-poor Cepheids, and this is quantified as the gamma coefficient in the period-luminosity relation. It's a small term, but we have to take it into account. And there are two main methods to derive this gamma term empirically. You can use a metallicity gradient. For example, even within the Milky Way, there's the gradient, and you can use it to trace gamma. Or you can compare different galaxies that have different abundances and compare the brightness of Cepheids. So this is basically the intercept of the PL relation in different locations. So in the Milky Way in red, and in the Magellanic Clouds in blue and green, as a function of metallicity. So Milky Way is more metal rich, and Magellanic Clouds are more metal poor. And it's overlapped with the Milky Way Cepheids in orange, which are binned because they're way more, but they're binned here, and you see basically the same trend, the same slope. And the slope of this line here is the gamma coefficient. Now, you're probably wondering what's the effect of this coefficient for the Hubble constant. Well, it's very low, it's very small, because even if you take different values for gamma, it doesn't change H naught very much. Here you have gamma on the lower axis and H naught on the upper axis. And whether you assume gamma is 0 or minus 0.4, it doesn't change more than 0.8. That's mostly because supernovae hosts and the anchors are very similar. Of course, there's the SMC and LMC that are more metal poor, but now we have Milky Way and NGC 4258, which are metal rich. So the dependency or the sensitivity with of H0 with gamma is lower. And here you have the consensus, whether it's in the near infrared in green or in optical in blue. The metallicity dependence is basically from minus 0.15 to minus 0.3. And the different shapes here show different methods. The gradients, comparing different galaxies using Gaia, and even the theory. However, there's one outlier here that I want to discuss today. It's by Medoret and Friedman 2025. They present a zero metallicity effect. So in order to understand where it comes from, we have reanalyzed the data and the method. So basically what they do is they get this flat gamma. They use also Milky Way, LMC, and SMC. In the Milky Way, they use a sample of cluster Cepheids, just like I mentioned before. But instead of using the official Gaia parallax, they adopt a magnitude offset to match the scatter of a previous PL relation shown in yellow here, based on FGS parallaxes on HST from 2007. So what we do is we adopt the same sample, but instead of this magnitude offset, we correct it with the official Gaia correction, which is additive in parallax space. And we can see it matches already the trend that we have seen before. And it also matches the internal trend within the Milky Way that is shown in pink. The second thing we did was, instead of taking the whole sample in the SMC, as they did in Mador and Friedman, we select only the core region and we reconstruct exactly the same trend we had before. So non-zero, negative, minus 0.2 mag per dex. So this is really reassuring, and we would like to highlight really that when using Gaia parallaxes, especially to really take care about the treatment of your parallaxes and adopting the Gaia official calibration. All right, so just before concluding on metallicities, I've talked about measuring this gamma effect, but how do we even measure metallicities? For nearby Cepheids, it's easy. We measure individual spectra because they're very bright, so we can do that in Milky Way and Magellanic Clouds. However, in supernovae hosts, Cepheids are much more distant, so we cannot have their individual spectra. Therefore, we rely on H2 regions. But these two methods are really consistent. They give the same results. This is a comparison of both methods in the Milky Way, and we can reconstruct the gradient in the Milky Way really well. So H2 regions agree with Cepheid spectra. And my conclusion on the metallicity dependence is that it used to be a systematic because most of the previous H0 measurements were based on LMC as only anchor, but now we have more anchors. And gamma is H0 is less sensitive to gamma now. And that's why the exact value of gamma has a very little impact. And we highlight that the gamma term should be measured with modern and consistent data as much as possible, and if possible, a large metallicity range. We can say now there's a good consensus on the value and the sign of gamma, and even if there are a few discrepant values, we are able to trace where they come from, and it's generally the treatment of parallaxes or the treatment of the SMC. And it's also confirmed with models. All right, so the second systematic I'd like to discuss is the crowding. So this is how HST and JWST observe Cepheids in supernovae hosts. HST is more sensitive to the background and the surrounding stars around the Cepheid, while JWST can resolve much better the nearby stars. So the crowding is a bias that used to be corrected for before JWST. using artificial star simulation. So we injected artificial stars and we remeasured them to correct for this bias. And it used to produce additional scatter in the PL relation, just like a statistical noise. But whether you correct it with artificial stars or use JWST, now it's a very minor issue. So I'll show you what we get with JWST. Just before that, just a reminder, we are now looking at these second rung galaxies. The first rung is not crowded at all. They're very nearby, so it's really not an issue. And here the goal is to remeasure all of these galaxies that have been observed with HST, but now get them with JWST. So this is an example of one Cepheid observed with HST compared to JWST, and we already resolved the background very well. And for the PL relation, this is one example, but we have many of them. This has been published in RIS 2023 and 2024 with more hosts. The dispersion is reduced by a factor of 2.5. There's a much better precision for distances. And more importantly, the agreement between HST and JWST distances is really good, which shows that crowding is not a bias for the Hubble constant. Even more interesting, among these hosts on the second rung, there's this one, and it's called the perfect host. This has been published in RIS 2025. This galaxy is really interesting because there's the main host, a spiral galaxy here, and it's dominated by old populations. So if you look at Cepheids here, there's a background, a non-negligible background. And then there's a tidal host, a tidal companion on the left. And this one does not have any old population. So you can see it here. There's basically no background. So technically there's no crowding actually. And it's a perfect environment to test the effect of crowding because they have basically the same distance. So you can make the period-luminosity relation in each of these hosts, which is what we did. And in addition to the great improvements from JWST in black, we reduce further by 50% the scatter of the period-luminosity relation. And this is actually with 0.12 mag, this is the tightest PL outside of the local group. For that distance, it's a really impressive result. And the small images here show for one Cepheid, you have the HST image. Then for the same star, the JWST one with much better resolution. And then obviously not the same Cepheid, but one at the same period in the tidal companion. And there's absolutely no background, which I think is really impressive. So in conclusion, about this host, what we can say is there's again great agreement between HST and JWST distances. And for sure, now this shows us that the crowding is completely ruled out as a possible source of the Hubble tension. In addition to having Cepheids, we also have more distance indicators in the same JWST data. There's TRGB, JAGB, and even MIRA. So here's a comparison from RIS 2024 between Cepheid, HST Cepheid distances compared to JWST for different methods. So Cepheids, TRGB, JAGB, and MIRAs. These are other types of stars. I'll say a few words about these methods in the next slides, but basically they're independent and they give consistent distances. And we use two teams data. Unfortunately, we only have one anchor so far, NGC 4258, but it's enough to give good conclusions. Really, these differences are nothing compared to the size of the tension, which would be 0.2 mag. So really, all these different methods agree in distances. There's also a question of which sample you select. So for TRGB, for example, we combine HST and JWST hosts, which gives us 35 supernovae. And we get 72 for the Hubble constant. And there's a paper by Sean Lee, 2025, that reanalyzes the subsample selection and CCHP gets a lower Hubble constant because their selection is different. They use a smaller subsample, and some hosts have been excluded, the ones in brown here. And we believe there's no reason not to use the full available data. And now, independently, there's another result, very recent, by another group led by Max Newman, using different supernovae, which are not in the CCHP sample. This time they focused on elliptical hosts, and they use ZTF supernovae, and they get a Hubble constant of 75 plus minus 3, which is, again, independent from SHOES or CCHP. All right, so I think now you see where this is going. Instead of comparing H0, which is very dependent on the assumptions you make, and especially the supernovae sample, something we should really do is actually look at the distances. So what I'm working on right now is comparing distances to nearby galaxies where HST performs the best, where we have low crowding and high signal to noise. I also like to say with HST, we have observed nearby galaxies like Milky Way, Magellanic Clouds, because they're used as anchors. And we have observed supernovae hosts. But in between, there's a whole range of nearby galaxies that we haven't observed. And HST can get amazing results there because the galaxies are nearby, and we have the opportunity to test all of these methods consistently in a very nearby environment. So the goal of this program is to expand the sample of nearby galaxies to observe Cepheids, TRGB, and JAGB consistently. So these are the few galaxies that we have observed. At least we have the Cepheids, and in some of them we also have TRGB and JAGB. And the goal is to add these new targets consistently, again, in the same set of filters, which is the HST with C3 system, the same as the SHOES team, so very consistent, and to take advantage of the low crowding and high signal to noise. So a few words on these different methods. For Cepheids, we observe 3 epochs with HST, and then we combine with ground-based light curve to correct mean magnitude. These galaxies cover different metallicities and extinction levels. Then we have the TRGB, which is completely independent. So basically, it's based on the color magnitude diagram, if you're not familiar with it. And basically, these are stars that become cooler when they reach the tip, and they go back down the red giant branch. And you measuring the tip gives you a measurement of the distance. So something that has been shown recently is that you can refine this method by calibrating the relationship between the contrast ratio, basically the number of stars above and below the tip, and the magnitude of the tip. So this should be calibrated even better with our sample of nearby galaxies. And then the last method is the JAGB, so the J region asymptotic giant branch. It's observed in the outer disk, and same as for the TRGB, is based on the color magnitude diagram. This time it's not a tip, but it's in the near infrared, and we observe the position of a grouping of stars, a clump of stars here, and the position gives you an estimate of the distance. And these are carbon-rich asymptotic giant branch stars. And same as TRGB, we plan to investigate the field-to-field variation. So if you look at one galaxy, but different field of view, you should get the same answer, you should get the same distance, but it's not always the case. So it's a great opportunity to calibrate the systematics of both of these methods. So I wanted to give some preliminary results, but it's still a bit early to give distances. Cepheids are mostly done. But we're still working on TRGB and JAGB. However, I'm not going to give distances, but I'm going to show you some plots. This is the phase-corrected, crowding-corrected PL relation in this host. It's basically the same scatter as the Large Magellanic Cloud, which is much closer. The scatter is extremely tight, and we have other galaxies, of course, with also very low scatter. So very good results. We fit the intercept, and we fix the slope to the SHOES value. For the TRGB, we also have extremely good plots, and we are currently working on measuring distances. We have way more. We have different pointings within the same galaxies. So this is ongoing work. All right, so my conclusion is that instead of looking at H0 values, really to improve our understanding of the systematics is really to compare distances where you have good quality data, especially nearby galaxies, and to compare the different indicators. So we expect the full data set in a few months, and hopefully a paper within next year. For the shoes distance ladder, currently the best estimate we have, the best constraint on H0 is from the HST distance ladder, 42 supernovae hosts, 42 supernovae, and 4 anchor galaxies, all observed consistently with HST. From JWST, we learned that distances are in excellent agreement with past HST data. And for sure, now crowding is not an issue anymore. And overall, Cepheids are extremely good standard candles. The metallicity dependence is well understood and well calibrated. And I'm really excited in the future for precise parallaxes from Gaia at ER4, both Cepheid and clusters. Hopefully, we can assemble a better catalog of cluster Cepheids and less systematics in Gaia parallaxes, less dependencies with the offset. And in the long term, after the ELT first light, the European ELT, hopefully we can measure more eclipsing binary distances to M31 and M33 to have, again, more anchor galaxies. So yeah, I'm happy to take any question, and thank you so much.
Thank you so much. Thank you. Very nice talk. Any questions? Alan?
Thank you for the nice talk. You showed a couple of examples where there was a very small scatter in the PL relation, and so I was just wondering, in the examples where the scatter is very large, is that large scatter understood? I guess some of it comes from metallicity, range of metallicity, but does that account for all of it, or is there some variation from galaxy to galaxy that's not fully understood?
Yeah, that's a good question. Thank you. I guess in the galaxies where there's the largest scatter, these are the galaxies that are the most distant. So there could be a dependence with metallicity that's internal to that galaxy, and photometric measurements as well. I guess there's also the instability strip, so you cannot get a infinitely thin PL relation. There's an intrinsic dispersion that will always be there. But yeah, I would say at larger distances, of course, it's harder to measure the photometry even with JWST. So yeah, but at nearby distances, we expect a super tight PL.
Okay, thanks.
Thank you. More general question then. What is your take on the Hubble tension? So what do you think about that?
Yeah, I think we have looked at many things, and it's super interesting to see that we are sticking to the same value. No matter what we do, it's really hard. As I said, with the variants, we have tried so many variants, and it's really hard to get below 72 or less. So yeah, I'm excited to test more systematics. Like I think the last one would be dust and the reddening laws. But after that, I think it's what we see is pretty clear, and it's hard to come up with more ideas of what to test.
Thank you. Any other questions? Yes?
Yeah, hi. I was wondering, you showed so for instance, you're saying that gamma cannot account for more than 0.8, but that's the mean value. Does it increase the error bars because gamma itself can have only by itself it's a physical parameter with error bars, and therefore it can increase the error bars in the Hubble.
Yeah, I think there is a scatter within these measurements, but basically even with large error bars, even if you look at all these measurements, they really agree within 1 sigma, and really the dependency between gamma and H naught is really the one shown on the top axis here. So really even with extreme values like minus 0.5, you cannot get below 72 again. Is that what you were asking?
More in the context of error propagation. So, if you have gamma, which is 0.8 plus minus 0.1 or whatever, 0.3, what will that affect? How will that increase the error bar of the Hubble parameter, not the mean value? So I guess, yeah, roughly. This is what you said.
I'm not sure exactly what you mean, but the fit of the Hubble constant is simultaneous between the 3 rungs, and both H naught and gamma are free parameters. And the fact that gamma might have a higher uncertainty does not really affect the Hubble constant. And because now we are fitting many anchors and many host galaxies, both gamma and H naught are simultaneously well constrained, I would say. So there's really no case where we have a large uncertainty in gamma. It's really basically minus 0.2 plus minus 0.1. And that's the pessimistic situation. But usually you can calibrate it even better. So I wouldn't say having large uncertainties in gamma would affect the Hubble constant in any way.
Okay, I have another question. Show the plot of Hubble versus JWST, where there seems to be much more scatter obviously in the Hubble. Yeah, I guess maybe this one. So yeah, so the average is the same average, and you just have larger scatter because it's the Hubble telescope instead of JWST. I mean, shouldn't we also have the same scatter but with smaller error bars for JWST?
Yeah, so we have a smaller scatter now because of the resolution of JWST, and before there was more crowding, even though it was corrected with artificial stars. And obviously it's much better to forget about the artificial stars, but have actual measurements with good resolution. And something I didn't mention is that they're not exactly the same filters, but with very good transformations, we can match them. So we can overplot them on the same diagram. But here it's a combination of filters in the near infrared that's almost the same. But yes, we are able to match the distances even with slightly different filters. So both the scatter decrease and the distances agree.
Thank you. Yes, Richard?
Hi, thanks for the very nice talk. I wanted to ask a question about the historical part of your presentation on the work reproducing Henrietta Leavitt's work. Where exactly did you start with this? Did you start from the notebook there, or did you go back to, let's say, something like the dash scans of the photographic plates?
Yeah, so thanks for your question. There's actually, there's a team at Harvard that works on digitizing the plates. We haven't used it, but we're thinking about possibly a follow-up using the digitized data. But we actually started from the notebooks. The image you see here was the starting point of the project. So we put all these numbers in a spreadsheet, and then we plotted the data to get light curves. So that's where we started.
Very nice. Did you, in the process, figure out how she actually selected down the 25 Cepheids from the 1777 variable stars she initially had?
This is not clear, I guess. I'm actually not sure why she picked these 25, but that's a good question.
Thanks a lot.
I think we can thank Louise again. Thank you so much. you.